Good afternoon. Welcome to the second talk of today. We are hosting Hilder Pereira. He's a postdoc at COSIC, University of KUL in Leuven in Belgium. And I have just received great news that he will be an assistant professor in Campinas University in Brazil, which is a prestigious university in Brazil. And we congratulate Hilder for receiving this prestigious position. Hilder is known for his work on fully homomorphic encryption. He has worked both in theory and practice of FHE, which he will be teaching us about the basics today. And he has worked on some constructions based on different assumptions such as approximate GCD, and also some assumptions which is a mixture between untruth type assumptions and LWE assumptions. Helger, thank you for accepting our invitation. We are very happy to hear your presentation. Please go ahead.
Thank you very much for the introduction. I'll just try to share the slides here now. So I hope you can see it in full screen now. By the way, can you hear me well?
Yeah, we can hear you and we can see your slides.
Okay, thank you. Okay, so today we are going to discuss the foundations of fully homomorphic encryption. And I hope this will pave the path for the next talks on FHE, the next two, right? Okay, so we will start with a very high-level introduction to FHE. And then after this, we will talk about some hard problems that are used to build FHE. And then we will really get into the core of this class, where we will see how we can actually construct FHE schemes. And finally, we will end with just some discussion about the state of the art and some libraries that exist and the schemes that exist and how you can choose them for your applications. Okay. So the main so why FHE was actually introduced, right? So we had this interesting problem of computing on encrypted data, and the classic example we have is like a hospital that has some data, and the hospital has the data of some clients, for example, and the hospital wants to store this data in the cloud so that the hospital doesn't have to take care of all the infrastructure and all the technical details of storing data, backups, and everything. So that the hospital can just encrypt this data and send it encrypted to the cloud, right? Because since these are data about the patients' records, for example, the hospital doesn't want the cloud to know this data, right? So the data can just be sent encrypted to there. That's fine. And then whenever the hospital wants to use some data, the hospital can just download this data, decrypt, and use it, right? But now the cloud can do much more than just store the data, right? The cloud can, for example, use the massive data that they have to train models, and then maybe this can even be useful for the hospital. For example, there are these news where some AI models, they were taking as input some data about cancer examinations, so data about tumor and other stuff, and then they could predict if a patient has a cancer or not, right? And this can be used to help the doctors in the hospital. So the hospital would like to use these capabilities that the cloud is providing, right? But how can the hospital use these functionalities provided by the cloud without revealing the data of the patients, right? Because the data is encrypted there, the cloud cannot do anything with the data, right? And if the cloud they'll download the data and decrypt it, well, then it's on the hospital download the data and decrypt it, then it's the hospital side, so the hospital doesn't know how to do this. So the solution to this is, well, at least one of the solutions is homomorphic encryption, right? So the cloud has to be able to do something like this. The cloud has to be able to take C, which is the ciphertext encrypting the data that the cloud sent, F, which is a description of the function that the cloud wants to evaluate on the data. So for example, a neural network keys, so any data that is public, that's fine, right? It's public, so the cloud can also use this. And using this, the cloud should be able to run some evaluation process. We call this just eval, that outputs a new ciphertext C bar, right? So this is important. This is also encrypted. It's a new ciphertext C bar. And then the thing is that this ciphertext C bar encrypts this function evaluated on the data that is encrypted on C, right? And this is also encrypted, right? It's just C bar. So now the cloud can send this ciphertext back to the hospital, and the hospital can now use this the secret key to decrypt the C bar and get the corresponding message, which is actually the function evaluated on the original data, right? So we say that we define usually this eval in terms of circuits. So this eval will just be, so let's say, a function that takes a circuit, a description of the function that we want to evaluate, a set of ciphertexts, right? Output a new ciphertext, and this is just what I explained, right? And then you can use the secret key to decrypt the ciphertext and get the function evaluated on the messages that were encrypted by these ciphertexts, right? And well, then we say that a scheme is then we say that a scheme is fully homomorphic if we can use this eval here to evaluate any computable function f, right? So essentially we can consider all the possible circuits here, right? So this means that this scheme is fully homomorphic. Okay. So we can see it in a graphic way, right? We have this, for now, it's kind of a magic.
Sorry, Hilder, can you hear me?
Yes.
So I see one extra thing on your slide. I don't know what it is. There is something on your slide.
One extra thing?
No, it's a mic icon. It's a camera icon. I don't know what it is. Okay, could you please close that? Yeah.
Yeah, I don't know if I can actually close it. I see. I see what you mean.
Where it comes?
It's from the browser, right? But is it?
Yeah. Can you move it or?
I don't.
okay,
maybe like this.
Yeah, that's better. So.
Okay. Thank you.
Thank you.
Thank you for telling me. Yeah. Okay. So as I was saying, right, this eval here, this is the procedure that the cloud will evaluate, right? So the client will just encrypt this the data, send it to the cloud, and then the cloud can have this, the red box here are encrypted, right? And then the cloud will take some description of the function, the public key, and use all of this as input of this eval, and then this outputs a ciphertext encrypting F evaluated on these values, right? So this is what FHE allows us to do, essentially, okay? And then, well, there are many, let's say, trivial applications of FHE. For example, you could encrypt a string and send it to your search engine like Google or DuckDuckGo, and so that they would send back to you ciphertexts, and when you would decrypt this, only you would know the query and the results. Right? The cloud would not know what you are searching for and would not know the results, for example, right? And well, there are many other examples, right? As I just said, any cloud can provide you machine learn services over encrypted data. And also there are many, let's say, more theoretical applications of FHE. So FHE is a very powerful tool, and you can use it to build or to improve many other cryptographic primitives. Right? For example, there are private information retrieval protocols that are built on top of FHE, and they are very efficient. Right? And there are many other examples. So you can see FHE, you can think of it like this, right? So it's a very powerful and general tool. It gives you an optimal two-part security computation protocol, because you just have to encrypt your data, send to the other party, and the other part can perform the computation and send it back to you, right? So it's really minimizing the rounds. And well, usually it's quantum secure because of the problems that we use to construct FHE, as we are going to see soon. And on the bad side, the ciphertext expansion is usually big. If you compare, for example, with block ciphers, right? So this means that when you encrypt your data and you send to the cloud, you send much more data than the original data that you had, right? So right. But there are some solutions to this, but we are not going to discuss it here. And it can be expensive to the client. Even encrypting and decrypting can already be a bit expensive if you compare with block ciphers or other primitives that are very efficient, right? So it can be expensive for the client, but it's for sure expensive for the server, right? So the homomorphic computation is usually much slower and much more costly than the computation in clear, right? But I mean, that's also kind of expected, right? You are doing something very powerful here. You are computing without knowing the input, right? So it has to be more expensive. And yeah, in general, it's hard to implement or hard to deploy in practice, but there is also a lot of ongoing work on this, and especially some companies are working a lot on this nowadays to make FHE more user-friendly, okay? So how FHE works in a high level. Each FHE scheme will offers you a few homomorphic operations. So for example, addition and multiplication, right? And you want to compute some function f. So what you have to do is you have to represent this function f using the operations that you have. Okay, so for example, I have this function f here, which is very easy because I want to give you an easy example. So this function is just x squared plus x, right? So let's say the homomorphic operations I have are homomorphic multiplication and homomorphic addition. So this translates quite naturally, right? So if I start with a ciphertext C encrypting X, I just use the homomorphic multiplication to multiply C by C, and then I get C prime encrypting X squared, right? And then I use the homomorphic addition and I add this X squared to X, right? So the output here will be what we want. And then, so this homomorphic evaluation, that box that I showed before, at the end, it will just be a sequence of these basic homomorphic operations that we have, right? So it will just be a long sequence of these operations. And well, one of the most important and annoying features or properties of the FHE schemes is that the ciphertexts are noisy. So what we mean by this is that when you just encrypt a ciphertext, the ciphertext you have has a small term on it that we call noise. So this is a small noise, right? And then every time you run one homomorphic operation, like a multiplication or homomorphic addition, you increase this noise. Okay, so, and at some point, if this noise is larger than some bound B, the decryption fails. You cannot decrypt the message anymore. Right? So you kind of have this situation here. You start fresh ciphertext with a small noise, and there is this bound B here that you know beforehand. You can estimate this, you can compute this bound given the parameters, right? And then you perform some operations, the noise grows, you perform more homomorphic operations, the noise grows too much, and now you reach the limit. So you cannot perform further homomorphic operations. Right? So this means that the number of operations is limited. It's not really fully homomorphic if the number of we can just evaluate circuits with a bounded depth or bounded number of gates. So we need some way to transform this bounded, that in the literature they are called somewhat homomorphic encryption or maybe leveled homomorphic encryption, into a really a fully homomorphic encryption scheme. Right? So what we really have to do here is we have to find some way to reduce the noise of the ciphertexts, right? So if you can perform operations, the noise is big, and we can somehow come back to here where the noise is small, then we enter in a loop, right? Then we can perform more operations and do the same, okay? So this is what we want to do. And this was Gentry's idea when he proposed the first FHE scheme. His idea is, well, this eval here, this box, I said that we can evaluate any function on it, right? So what about if we evaluate the decryption of the scheme itself? How this works? Well, we have the ciphertext C here that has this big noise. We want to reduce its noise, right? We take an encryption of the secret key, and these are the two inputs of the decryption, right? So now we run this eval box here using this decryption and these two inputs. And the output is a ciphertext that encrypts the decryption evaluated on C and SK, right? But this is the message. The decryption removes the noise and gives us back M, right? The message. So this operation will reduce the noise. It will completely remove the noise of C. So what's really happening here is we are taking the ciphertext C with full noise, and we are taking the encryption of the secret key with very small noise. This decryption here internally totally removes the noise of C, right? It actually transforms C back to M, so there is no noise anymore. But this evaluation is increasing the noise that we have here in the secret key, so that at the end we have something like middle noise, right? Let's see, the noise is close to the middle, right? So this is what we call bootstrapping. The bootstrapping consists in evaluating the decryption function homomorphically on a ciphertext that encrypts the secret key with very small noise, and then it outputs a new ciphertext encrypting M, so the same message that the original ciphertext encrypted, but now with a small noise, right? Much smaller than what we had before. Okay, so as I said, this gives us this loop here, right? So, okay, so now we have this. We can perform some homomorphic operations. If the noise gets close to the limit, we bootstrap, right? We evaluate the decryption homomorphically, and then we go back to 1, keep performing more operations, and we are in this loop, right? That's nice, but, well, the problem is that this bootstrapping is usually very slow, and also that it requires a lot of key material, okay? So we have this scenario now. I don't know if you already have any questions. Maybe you can ask now, otherwise I can continue.
Questions?
Question, a simple
Yes.
one, Hilder. So
Yes.
you mentioned that we have this noise problem. So it seems that
Yes.
it comes from the lattices, that we have this problem in the lattices. But have you thought about if it's possible in future, even as a dream, that to build such constructions based on different assumptions, or even people haven't tried to do something alternative?
Yes. There are some. Well, I have seen very few attempts to construct FHE based on problems that don't involve this noise term, right? So probably this means that a lot of people are trying and they are not getting anywhere, so they don't even have a proposal to publish, right? Because it really looks hard to construct it without the noise. Even the other assumptions that we use, N-true or AGCD, I'm not going to talk about them here because they are not the main assumptions that are used to construct FHE, but all the assumptions that are really used to construct FHE involve this noise term.
I see. Thank you.
Okay, so let me continue now. So, okay, this was just a high-level introduction, right? Yes.
There is one question, Shahram. I thought that you were asking that. So there are 2 questions in the chat. Maybe Shahram can answer.
So let me ask. So somebody has asked, is there any threat in using of bootstrapping several times?
No. So, the FHE scheme, it's secure even if we run this evaluation, homomorphic evaluation for any function, right? So in particular, it's secure if you evaluate for this decryption. So the only detail, let's say, is that here you see that I am encrypting the secret key, right? But I am encrypting the secret key under the secret key itself, okay? So we call this circular security. Most of the times we cannot really prove that this scheme is circular secure, but we just assume that it's circular secure, right? But, well, this is seen as a very weak assumption usually, okay? So, okay, so in summary, no, there is no problem. You can evaluate the bootstrapping as many times as you want, right? The only problem, otherwise it will take a lot of time to evaluate your function.
Yeah. So there is another question, but I think you already answered it. So if he has asked or she has asked if the same key is used for bootstrapping or different evaluations.
Yes. Yes, so you this is what I just said, essentially, right? You use the secret key, you encrypt the secret key under the secret key itself. So,
yeah. So it will be part of the public key.
Sorry?
It will be part of the public key, these encryptions of the secret key.
Yes. Well, yeah, so this is what you can send to the server, right? It's just let's say a ciphertext or a set of, at the very end, it will be a set of ciphertexts because we encrypt it in a nice way such that this evaluation gets easier to be evaluated. But yeah, we will just send this to the server, so we could consider that they are actually here, right, as part of the public key, because the server will use the same all the time.
Yeah. Okay, thank you. Let's continue.
Okay, thanks for the questions. Okay, so now I gave you a high-level intro, right, about FHE. The goal is to really have a good idea of how this FHE works, right, under the hoods, let's say. So first we will start trying to understand a little the two main problems that we use to construct FHE, right? These two main problems are called learning with errors. This is known as LWEE, and the ring learning with errors, which is you use some polynomial rings instead of just vectors, right? So these are the hardness assumptions. We assume that these problems are hard, and then we can construct the FHE schemes, okay? So what is this LWE? Well, let's start with this easy to solve problem. Huh? So let's say you just fix a dimension n, it's just an integer, right? And another integer q, which we will call the modulus, right? And then I can choose a secret a polynomial s of dimension n and entries modulo q, and I keep this vector secret, okay? Now, imagine that I compute, let's say, multiples of this vector s. This means that I sample other vectors a uniformly, right, from dimension n, coefficients mod q, and I compute this inner product, right, a times s. So this gives me an integer bi, right? So I use the same s for every I, right? And then I give you many pairs like this. I'm giving you a and I'm giving you b, ai and the integer bi, and I ask you if you can recover s. Well, you are a smart guy, so you realize quickly that you can just put all these vectors here, and you actually have a matrix if you do this, right? And then you put the corresponding integers here, and you have this vector, and now you know that by construction, this a and this b, they satisfy this relation, right? A times the secret s is equal to b modulo q. So this is linear algebra. We know this since we are babies. You can just solve this linear set of equations and you get this s again, right? So this is very easy. You can just quickly find the secret s. But what about if instead of having just a times s, this is multiple, so to say, now we add a little error here, right? We add a little integer here. So I still sample this a uniformly at random. I still multiply this a by this secret s, but I'm adding this small noise. This is the small noise we're talking about, right? Now this b is not exactly a times s, but a times s plus some small integer, right? Now I ask you to recover s. Well, if we try to do the same trick, you construct this matrix A and this vector B. Now they satisfy this relation here, right? A times S plus E is equal to B. But you don't know S, this is what you want to find, but you also don't know E. Right? So now you cannot just use linear algebra to solve this problem and find S, right? Because you don't know E. And even if these values here are small, this is a hard problem to solve. So this is the learning with errors problem. It's the problem of recovering S if I give you many samples A, B of this form, right? A times S plus E is equal to B. And this is a hard problem. All the algorithms to solve this problem take exponential time, okay? So this is one of the main problems that we use to construct FHE. Okay, and now the ring learning with errors is kind of the same, but instead of having vectors here, what we have are polynomials, okay? Which is a power of 2, okay? And then we can define this ring R. This is just Zx here just means polynomials on variable x and integer coefficients, right? And then I take this modulo x to the n plus 1. So this means that this R is just a set of integer polynomials with degree less than n, okay? And then if I fix a positive integer q, I can now define this RQ essentially as the same as R, but now the coefficients are modulo q, right? So RK is a set of polynomials of degree less than n and coefficients mod q, right? So if, for example, n is 4, it's a power of 2, okay? Q is 7. This RK would just be the set of polynomials, right? So A0, A1, A2, right? These are the coefficients. So polynomials with degree less than 4. And all these coefficients, the AIs, belong to ZQ. So this means they are between 0 and Q minus 1, right? Okay, so first we fix these parameters to define this problem. We have to fix n and we have to fix q to define this ring learning with errors, RLWE. Okay, and then how it works now is we have a secret polynomial now instead of a secret vector, right? And again, let's do the same. Let's say I just take random polynomials and I compute this polynomial b as a times s, right? Multiplied by the secret polynomial. And I give you all these pairs. Now, basically, you can do the same, right? You can use linear algebra to recover s, or even if one of these a's is invertible, you can just take this b here, multiply by the inverse of a, right? And then you cancel away here, you get back s, right? But as before, now, instead of just a times s, we have a times s plus some small noise. So now this e here is a polynomial as well, right? Polynomial r. And now if you try to do the same, you multiply by the inverse of a here. You cancel out a, so you get s. That's nice. But you have this term here, which will be huge, close to uniform, actually. And then you will not be able to recover s like this, right? So again, this is a hard problem. So this is what we call the RLWE problem. I fix a polynomial. I can sample many uniformly distributed polynomials AI. I sample small noises E from some distribution. Usually they use a discrete Gaussian distribution. And then I define this PIs like this, right? AI times S plus the noise. And the RLWE hypothesis says that if I give you many pairs like this, you cannot distinguish them from pairs that are truly random, right? This is the RLWE hypothesis. And
Hilder, I have a question.
yes.
So you have introduced two assumptions, LW
Yes.
and RWE. For achieving the same level of security, let's say 128-bit security, so how do you compare the efficiency of these two assumptions in terms of samples, modulus, or I want to know that what is the point of introducing RLWE?
Yes. Okay. Okay. Thanks. That's great. Yeah. Essentially, for 128, any security level that you choose, this dimension here that we have, right, n, and this value q, they will be essentially the same as this new dimension, let's say, which is the degree n, and this value q. They will be essentially the same, right? The whole point is that here, this b is an integer, right? Because we compute the inner product of two vectors, right? So for the LWE, this b is an integer. This means that you can only encrypt one single integer here, right? You have to add your message here. We will see this soon. But for the for the RLWE, this b now is a polynomial. So you can add a polynomial to it. This means that you can encrypt n messages instead of one.
Okay, so the way that I understand is that let's say, so your polynomial will be of degree n, right? And you can then encrypting n messages using LWE separately.
Yes. Yes.
This is the point, right?
Yes. Because with the LWE, For the same N and Q, essentially, more or less, you can encrypt just one message, right? And here, for N and Q, you can encrypt N messages.
Okay, thank you.
So the ciphertext size is the same, more or less, but the ciphertext expansion, right? The size of the ciphertext divided by the size of the message is much smaller, right?
Okay, okay. So this is the point. So there is also a question in the chat box.
Yes.
While computing a function, how does one decide to bootstrap the ciphertext?
Yeah, okay, that's a good question. Well, we know this bound, the correctness bound beforehand, right? Just given the parameters, we can compute. We will see soon how to compute this bound, okay? So we can compute this bound beforehand. We also can estimate the noise of the fresh ciphertexts, okay? And then we estimate how each operation increases the noise. And this means that for any given ciphertext, if we know how many operations we performed on the ciphertext, we can estimate what is the magnitude of the noise that is inside the ciphertext. Right? We don't know the ciphertext, we don't know this value E here exactly, but we have an estimation of the norm of E, right? So if we have these two information, we can just decide when we get close to the bound, the decryption failure, and then we bootstrap, right? I think this will be clear soon because we will see some examples.
Okay, let's continue, please. Thank you.
No worries. Okay, so one nice thing about these two problems, the LWE and the RLWE, is that we have this worst case to average case reduction. So they are very famous because of these, actually. Right? Even outside of FHE, you can construct other schemes that are not homomorphic signatures, any other schemes based on the LWE and RWE, then you can take advantage of this to argue that your scheme is really secure, right? The point is, there are these old LATSE problems like the shortest vector problem. They are well known. They have been studied a lot, right? So for these problems, we really believe that they are really hard, right? And the LWE and the RWE, there is a relation between them and these LATSE problems, right? What we know is this was parameters N, Q. Then you can solve some approximate versions of these LATSE problems like the SVP with some approximation factor gamma, where gamma is, let's say, of the order, right? It's a big O notation, order of this Q divided by N, right? And then we have, so this gives us confidence on the hardness of our LWE problem, depending on gamma, right? Because we know that when gamma is 1, then we just have the original, the standard exact version of SVP, right? If gamma is 1. Then this is actually NP hard. It was proved, right? It's NP hard. As we increase gamma, if gamma gets close to n log n or square root of n log m, it's not believed to be NP hard anymore, but it's still all the algorithms that solve the SVP for these approximation factors, they take exponential or even super exponential time, okay? And as you increase this approximation factor here, gamma, usually you get to this region where the gamma is polynomially big in n, and then they are most probably not NP hard. This problem is most probably not NP hard, but it's still very hard to solve, right? If you want to solve the SVP with this approximation factor, this is very hard to take exponential time, right? At some point, gamma will be exponentially big, then this problem becomes very easy. There is an algorithm which is called LLL that solves the SVP with exponential approximation factor and polynomial time, okay? So this region here, right? This is what you want to do. when you instantiate your problems. Okay.
So what is this big Q here? Is it the modulus? Or?
Yes. I see. I switched the notation. Yeah, it's the modulus, right? And these parameters of the LWE.
Okay.
Okay. So these already give us a hint, some hints about. This actually explains everything about how these parameters influentiate the security, right? If you see that, just think of this Q here as a fixed value, and then you are increasing N. So this gamma is getting closer to 1, right? So this means that your problem is getting harder, right? Now, if you are increasing Q instead, then you are getting to this region here, and your problem is getting easier, right? So for the LWE and the RLWE, increasing Q makes the problem easier. Increasing N makes the problem hard, right? So increasing Q, less security. Increasing N, more security, okay? That's how it goes. So in practice, what we actually do is...
Oh, sorry, can I ask a question? So
yes.
Why shouldn't we just simply choose Q equal to 2 and work with...
Yeah. Because we want some space for the noise, right?
Okay, yeah.
This,
but
we will
still
see...
you can choose Bernoulli noise with some parameter in this case too.
If you just care about the problem itself, yes. But if you want to construct something on top of the problem, then no. Then you really have to choose a big Q, right? We will see this. This will become clear when we get to this part, constructing FHE. Okay.
Okay.
But I see what you mean. Yeah. Like just from the security point of view, we choose Q equals to 2, right? This problem should be hard already, right? Okay, so how it works in practice? Well, in practice we don't go to the SVP. We just check the algorithms that are used to solve the LWE and RLWE, right? So we just pick parameters such that the best attacks take exponential time, right? And to choose this parameter, it's standard. We use this tool that is called the lattice estimator. So if you are going to do anything that uses LWE or RLWE, it doesn't matter if it's FHE or any other type of primitive, you go there for this, you use this tool to pick our parameters, right? So as I said, you increase N, you increase the security, you increase Q, you reduce the security, okay? So if you have any questions now before we start the next part, because this will be the toughest. I think someone is asking about...
Yes, I guess you are reading this question. That's good.
Those parameters come from the variance of the error being added or multiplied. Yeah, I'm not... Yeah, okay. I see. It's because I'm trying to simplify a little here, okay? I just wrote this distribution here, huh? How you... Then you choose some variance for this discrete Gaussian, right? So this would be a parameter sigma, right? And then you know that this E here is small because it's close to the sigma, and you choose the sigma to be small. This would add another parameter here, let's say sigma, but the point is you cannot, most of the time you just choose the sigma to be a small constant, and then it's hidden in this notation, okay? So in the end of the day, you are really caring more about N and Q, right? You just try to choose this sigma as a small constant, and then you are just caring about N and Q, okay? So these are just the parameters of this problem, right? I don't know if you have other questions. If not, I will continue.
No, we can continue. Thanks.
Okay. So now we will see how we can use this RLWE to construct fully homomorphic encryption schemes, right? Well, the secret key will be the secret polynomial of the RLWE, okay? So we just pick this as polynomial S from this ring, and we use it as the secret key. We need a new parameter to control the plaintext, the message space, right? So we choose a new parameter T. It's just an integer, and we call this the plaintext modulus, right? So in the RLW problem itself, there is no T, right? There is N and Q, but for the encryption scheme, we need this extra parameter. Have this form A times S plus E, but it's still fine if we multiply this E by this parameter T, right? We can still prove that this will essentially behave as uniform is if the original RW sample behaves as uniform, okay? Part here, so what remains is T times the noise plus the message, right? All of this is modulo Q, right? We are always working modulo Q here. But we have this old trick that if a value is smaller than mod Q, than the Q, when you compute it mod Q, you get the value itself, right? So I don't know if this Q is 10, if this value here were 11, then mod Q, it would be 1. But if this value here were 5, then mod 10, it would be 5 again, right? So if this value is smaller than Q, this means that performing the mod Q means performing nothing. And then what you get is that this E prime is actually equal to the value that you have here on the right, without the modulo Q. So I'm saying here, if the norm of this value here is smaller than Q over 2 instead of Q, because we actually want these values here to be signed, okay? We don't only want values here between 0 and Q, but we also want a sign. So that's why we need to divide by 2 here. So if this holds, this E star is actually equal to T times E plus M over the integers, right? And then we can just compute E star modulo T, and we are removing this multiple of T here, and we are getting back M, right? So that's how we can decrypt. But you see that we have this correctness condition here, right? This is basically telling us, if we, let's say, simplify a little, this is basically telling us that this noise that we have in the ciphertext has to be smaller than Q divided by 2 times T. Okay, so that's the correctness bound I was talking about before, right? You always have to guarantee that your noise is below this bound, or otherwise your decryption will not work. Okay, so as I said, you can compute this bound just using the parameters that you set, right? You don't need to use the secret key, you don't need to use the ciphertext, nothing, right? It's just easy formula using the parameters. This is the correctness bound. And then you have to guarantee that your ciphertext, the noise in your ciphertext, always respect this bound. Okay, we have to remember this. Huh? We have to remember that we need this correctness condition here. Otherwise, we have a decryption failure. Okay, I said, well, the polynomials are a pair of, the ciphertexts are a pair of ring elements, right? So this A is an element of this ring, and this B is an element of this ring, right? But it's actually more handy, let's say, to represent the ciphertexts as a polynomial again. So we introduce a new variable y here, right? And then just not to complicate things, forget for now that this RQ is also polynomials, right? Just think of this as any set, and then we have that the ciphertext is actually a polynomial over this set with this variable y, okay? So our encryption outputs a pair of ring elements. This means that it outputs a polynomial like this, right? 2 coefficients. So polynomial of degree 1 on the variable y, okay? And then connecting with what we had before, this A here will just be C1, but now we put this minus here. It's equivalent, it's the same. It's just more handy to work with the equations for what we are going to explain soon, okay? So the encryption is just taking M and outputting a pair of elements as before. The first element is that B that we had before, right? The RLWE sample plus the message. And the second element is just minus A, okay? So now this ciphertext has this property. If you want to decrypt, we just have to evaluate the ciphertext on the secret key, right? So if we replace Y here by S, what you get is C0 here minus A times S, so this disappears, right? And what you get at the end is just the noise plus the message, right? So a ciphertext, you can see it as this polynomial of this variable Y, and to decrypt, you just evaluate on S, right? Yeah, and then you compute mod T, okay. But the important thing to remember is if you evaluate the ciphertext on S, you get the message plus the scaled noise, okay? Now, let's see how we can add. What is the homomorphic addition? Well, we can just add our ciphertexts actually, right? If you take our ciphertext, D at S, you are evaluating both of them at S, right? And we just saw that when we evaluate them at S, you get the noise plus the message, and then the noise bar plus the message bar, right? And you group terms here, and then what you have is T times the noise, the addition of the noise, plus the addition of the messages, right? So this means that this D, this new ciphertext, is really encrypting the sum of the messages, but now we increased the noise a little, right? The noise now is the sum of the noises that we had before, okay? But we can see it's pretty simple to add two ciphertexts. Now let's say we want to multiply. We want to compute the homomorphic multiplication. Well, this will be much more complicated, but let's start simple. So to have a homomorphic addition, we actually just added the ciphertexts, right? So let's try to do the same. Let's just multiply the ciphertexts. Then what happens? Well, then we are computing this, right? C times C bar. Because both of them had degree 1, now we have something on degree 2 on Y. Okay, so we can write it like this, okay? And we see that if we evaluate this D on S, we are evaluating both of the ciphertexts on S, right? So what we get is the noise plus the message times this noise bar plus the message bar, right? And well, now you just distribute the terms, you compute here, you see that the only one that is not multiplied by T is M times M bar, right? So this is out, all the rest is multiplied by T. So this D here is really of the form, has really the format that we want, right? When we evaluate it on S, we get T times something, this is the noise, plus the product of the messages. So this D is really encrypting the product of the messages as we want. But we have two problems here to remember. First problem, the noise is growing really a lot. If we say that this E here and this E bar, both of them have magnitude close to some B, now we have magnitude close to B squared, right? So this is really a lot. And also, the size of the ciphertext itself is growing, right? Because before we had degree 1, and now we have degree 2, so we have 3 components now, right? So these are two problems that we want to solve, okay? But let's say we just try to use this homomorphic multiplication as it is. Now, f of x, y, and it's just adding x to y and computing the fourth power of it, modulo t, right? If we wanted to do this, we would start with two ciphertexts, so one encrypting x, the other one encrypting y. And let's say that the noise, both of them have noise close to some sigma, okay? Then, how we would perform the homomorphic evaluation in this case? 3 steps, right? First one, homomorphic addition. We just add the 2 ciphertexts. This will give us an encryption of x plus y, okay? And then homomorphic multiplication. Now we have x plus y squared, right? And then we multiply this u by itself. So we have square times square, we get the 4th power, okay? And what's happening here is the degree we have here for after the addition is still 1, right? Because just adding polynomials don't increase the degree. But now the multiplication here increases the degree to 2, and the multiplication here increases the degree to 4, right? So you can see where it's going. And the noise here in the beginning, it was close to sigma. If you add, then we get noise close to 2 times sigma, right? And in the second step, we multiply this by itself, so we get close to 2 times sigma, but the square of this, right? So this is 4 sigma square. And in the second step, we take the square of this again, so we have 16 times sigma to the 4, okay? So you see, I am now doing what I said before. I am estimating the final noise that I will have with this homomorphic evaluation, right? So this is what you have to do. And this is the homomorphic evaluation that you are going to run. And you try to follow how the noise will grow with all the operations. And then you have an estimation for the final noise, okay? So as we saw before, the final noise has to be smaller than Q divided by 2 times T. Otherwise, we have decryption failure, right? So this essentially means that we have to choose Q close to 2 times this, so 32 times T, right? And the sigma to the 4 that we had here. So just to give you some concrete numbers, if we had chosen this sigma as a very small value, like 3.5, for example, and then this ciphertext, the plain text modulus to be 1 byte, right? Then we would have this Q here, which is close to 2 to the 21. So this means that from the homomorphic evaluation and the initial noise, we can estimate the final noise. From the final noise, we estimate the ciphertext modulus, right? And now the degree n is free, right? For now, it's still free. So what we do now, we choose a security level, and from the security level and from these 2 values that we already have, we use the lattice estimator I talked about before to find the value of n, okay? So if you plug this value here, 21 for log Q, right? The sigma and this lambda in the lattice estimator will end up giving you this 1000, 2 to the 10, right? And then your cyclotomic ring will be this. So you will be working with ciphertexts over this ring, okay? So that's how it goes to estimate the parameters and to find, to estimate the final noise and to find your parameters, okay?
Hilder,
yes?
It is not clear for me if you necessarily had used the LWE, what would be the benefits? Because
the LWE instead of the RLWE?
Yeah. Then there you could have only your message space was integers, right?
Yes,
Modulo,
yes.
Modulo T. But
yes.
now you have n ciphertext, which is encoded as a ring element. So your ciphertext is a ring element here, which is essentially n.
A ciphertext is a pair of ring elements, right? It's a pair.
No. Your plaintext. Sorry, your plaintext is.
My plaintext is a ring element. Yes, modulo T.
Yeah. So which encodes n.
A disadvantage, right, of LWE.
Yeah, but what I don't see where the efficiency comes in. Is it in the size of the ciphertext? If instead I had used LWE, but for encrypting a message from this ring, I had to run the encryption on each coefficient of the
yeah.
polynomial individually. So
Yes.
how worse it would be?
Well, you would multiply the size by n, right?
Yeah, yeah. So here also you are multiplying the size by n. So I don't see what's the point.
No. Because the ciphertext with LWE, let's just go back here. The ciphertext has dimension n, right?
Yeah.
With LWE. Dimension
Okay.
n, but just encrypts one element, right? The other one has dimension n, but it encrypts n integers, right? So if you want to encrypt...
But the dimension n is actually, each of them is composed of n elements itself, because you are working on the ring. So I don't see...
Yeah, but n elements encrypt... for the RLW, you essentially have dimension n, but you encrypt n integers, right?
Yeah.
For the LWE, you have dimension n, but you just encrypt one integer.
No, but in the RWE, you are the length of the ciphertext is increasing by a factor of capital N.
The length of the ciphertext is n.
Yeah.
N log q.
Okay. And
it's 2 times n, right? Log q, right?
Okay, so here you have capital N.
Yes, but capital N is essentially the same as the n we had here, except that I am restricting myself to powers of 2, right? So if this n here, for example, were, let's say 900, then this capital N here would not be 900. It has to be the next power of 2, right? But they are still close to each other.
Okay, and you are saying that choosing a small n and capital N to be the same value, you get the same security level.
Yes, essentially, yes.
Okay, thank you.
Yeah, so you gain like this, right? If you want to encrypt 1,000 values in this example here, right? You can encrypt 1,000 values into one single ciphertext, right? But with the LWE, you have to use 1,000 ciphertexts to encrypt your 1,000 values, right?
Okay, I see.
Okay, there are also other things, because here, as I explained, all of this trick here, this worked fine because we can multiply these polynomials, right? You see, over LWE, it's harder to define the homomorphic multiplication. We can still do this, but it's harder. We have to use tensor product instead of polynomial multiplication. So there are also other advantages in using the RWE. Okay, so far, right? We know how to add and multiply ciphertexts, actually. That's nice. We already have 2 homomorphic operations, but the noise is growing exponentially, and the size of the ciphertext is also growing exponentially, right? So what the efficient FHE schemes do is they try to solve these 2 problems, okay? So let's see how we can solve this. Sorry, Karim, when is the class ending, actually? Because of the questions, I think I lost a bit track of the time.
So we have 1 hour left, I think.
Okay, fine. Yeah, that's what I planned. It's fine. Thanks.
There are questions in the chat. I don't know, Shahram, would you like to ask, or you can postpone whatever you prefer?
So let me ask it. You have AS equal to B. With this, you can recover S from B. If given A by Gauss elimination, adding noise term A, it becomes a difficult problem to recover S. So this is the answer, I think. So somebody has answered? Or
yeah, that's exactly it, yeah.
So here is the question. Why we need addition of noise in homomorphic encryption?
Yeah, that was the question, and the next one was the answer, yeah.
Yeah, so
we can go on. Okay, so we have these 2 problems, okay? As we saw here, like the noise is growing exponentially, right? We performed 2 levels of multiplications, and this is the noise, right? Power 4. and also the degree is going exponentially, right? So we have to solve these two problems. So the idea to solve the problem about the noise is called modulo switching, okay? The idea is the following. So we saw that if the noise is close to some value b, after the multiplication, we have noise close to b squared, right? The idea is somehow, let's say we can divide the ciphertext by this value b, right? And if we do this, somehow again, the noise will also be divided by b. So what will happen is we'll have now a new noise E mut prime, but this will be equal to the noise E mut that we had here divided by b, or at least pretty close to it, right? So b squared divided by b give us b again, right? So if we can do this, somehow the noise will always be close to b, right? It will go to b squared and go back to b. Right? This is what we would like to do, but when we do this, what happens is that the ciphertext modulus q is reduced from q to q over b. Okay, but we can do this. Huh? Okay, let's assume for now that we can do this. Somehow we can divide by b, and we are reducing both the noise and the ciphertext modulus by b. Okay, if we can do this, what is the point? Only with multiplication gates, and if the inputs have noise close to b, the output of the first layer has noise close to b squared, right? And we multiply b squared times b squared, we get b to the 4, right? And then b to the 8, and then b to the 16. So with L levels, the final noise will be bounded by b to the 2 times b to the power of 2 to the L, right? And because of this decryption failure, we need this q to be larger than the final noise, right? So this means that log of q has to be larger than log of this power of a power, right? And then we drop this 2 to the L here. So what we get is that the log of q is exponentially large in L. Right? So with the current homomorphic multiplication that we have to choose very large q, right? The number of bits will be exponential, and if you remember what I explained in the beginning, if we increase q, you decrease the security, right? So you don't really want this, right? We want to do better. And let's say we can do what I just said. Now we will start with noise b and ciphertext modulus q. You multiply, you get noise b squared and modulus q, but you divide by b somehow, right? You divide by b, the noise goes back to b, and the ciphertext goes to q over b, okay? So this will happen for all the gates in this first level, right? And now if you multiply them again, you are now working modulo q over b, right? The noise will also go to b squared, but if you multiply by b, b squared, right? You do this again, you get always noise b, but now the ciphertext modulus is reducing, right? So you see that what you are doing now is keeping the noise kind of constant and reducing the ciphertext modulus, right? And now it's where the magic happens, right? With L levels now, the final noise is still b, but the final modulus is q divided by b to the L, right? Before we had the noise was b to the 2 to the L, right? Now we just have L. So for the correctness, to avoid the decryption failure, right, we need this final modulus to be larger than the final noise, right? So we need this inequality here to be true, right? Final noise is q divided by b to the L, and this has to be bigger than b. Okay, so this means that Q has to be bigger than B to the L plus 1, right? This is much better than before, because now you take the log of Q, you can see that the log of Q is just L plus 1 times log B. So log of Q is now linear in B, right? Oh, sorry, L, right? Before, with this naive multiplication, log of Q is exponentially large L. But now, log of Q is just linear in L, right? This is way, way better, right? If now you can set a high depth here, and it's fine because you are increasing Q just linearly, okay? So that's the idea of this modulo switching, right? Multiply, noise goes to square of what you had, you divide, go back to the original noise you had, but you are reducing the ciphertext modulus, okay? But well,
so, sorry, Hilder. So I don't really see the connection, LWE or RWE problem. So there you had the security depended on Q divided by N, right?
yes. So
what is this capital Q divided by B? How is it related to?
No. This is just telling us what is the value of Q that we have to choose, right?
Yeah.
Just like in this example I presented here, we saw that the final noise was like this, so we had to choose Q larger than this, right?
Okay, and now you are saying
so if you remember the RLW problem, if we choose a big Q, the problem will not be secure.
Yeah.
Right? So now with this modulo switching, we will be able to choose a Q that is much smaller, right? It's just B to the L instead of B to the 2 times to the L, right? So this gives us more security.
Yeah, but I don't really understand the magic that is going on here just by dividing the modulus to a number which is depends on the bound on the noise. So yeah. I think there is some magic here. So
yeah, the trick is just that here you are increasing the noise exponentially, right?
Yeah.
But here you are decreasing the modulus linearly, right? Essentially.
Okay. But somehow you are dividing the modulus in the method, or are you explaining it? Are you going to explain it? So if you have
yes.
So if you have a number added plus a noise and you divide it by B, so it's right. The modulus and the noise are both of them are divided by B. This is the point.
Yes, exactly.
Yeah.
So this is just a high level, right? But to see how this is really done, well, I will simplify a little the explanation. So
okay,
we have to consider that this pair now, this is the ciphertext, right? Remember, the ciphertext is a pair, right, of ring elements, right? Before I said we had this noise multiplied by T, right? By this scaling factor, right? Q over T. There is an easy way to transform from one format to the other. Essentially, you just multiply by something close to this delta, and you get that this will be canceled out, and you will get E, and then you get delta there, okay? But this, with this format, is easier to explain the modulo switching, okay? So let's consider like this, right? This is the ciphertext. The modulo switching, actually, with this format, is very simple. Everything you have to do is you take your ciphertext AB and you output a new ciphertext A prime B prime. Now the modulo is this Q prime, which is Q divided by B. Okay, so you have to assume that B divides Q. Okay. And so what you do is you just take your polynomial, you divide every coefficient by B and you round. And you do the same for B, right? Divide every coefficient of this polynomial B by the capital B and you round, okay? If you round, you get integers coefficients again, And then because you are also dividing the Q with this process, everything will be well defined modulo Q prime. Okay. So if you want to check that this procedure outputs a valid ciphertext, what we want to check is that this B prime is actually equal to this, right? This B prime is this A prime times S plus some noise plus the message times this scaling factor here, right? So just to simplify things, I'm assuming here that T divides Q prime, okay? But it doesn't really have to be like this, but it would complicate it a little bit, the maths here, for no reason, okay? So to see that this is true, so we want to check that B really has this format, right? To see that this is true, it's actually pretty easy. We only have to use this trick. For every real value, we know that if we round this real value, what we are doing is adding a very small value here that are between minus 1/2 and 1/2, right? So for example, if U is 1.9, when you round, what you are doing is adding 0.1, right? If U is 1.3, when you round, you are subtracting 0.3, right? But if this is true for real numbers, this is also true for polynomials with real coefficients, right? When you round every coefficient, what you get is that you have the original polynomial plus some very small polynomial where every coefficient of this polynomial belongs to minus 1/2, 1/2, okay? We just have to use this trick to see that this B prime really has this form. So what do we do? Well, let's define this Q prime like this, right? And then we see, by definition, right, this B prime is just rounding B divided by capital B. So if we use this trick, we have this, right, for some epsilon. Now we use the definition of B. The definition of B that we had before is just this, just minus A times S plus the noise plus this delta times M, right? All of this is divided by B, right? So now what we have is A divided by B. The noise is divided by B as we wanted, right? That's nice. I'm just adding this epsilon here because it's part of the noise now. And we see that this Q divided by B is now Q prime, right? So we already have this term here as we want. We have some noise, but we don't have A prime here yet, right? We have something, but not A prime, okay? But now we just use this trick again. If you just notice that A prime, by definition, is this rounding here, right? So this is just A divided by capital B plus another small polynomial epsilon prime, right? Then this A over B here is just A prime minus this guy here. Minus this epsilon here, right? So if you just replace this here instead of A over B, you get A prime times S, right? And you get this epsilon prime here times S, okay? And all the terms that we had before, 1, 2, and the message, okay? So now we can really see that this B component, A prime times the secret, plus some noise, and the message is scaled as it should be, okay? So it's pretty simple, right? You just divide by the value we want, and you round both components, and this will work, okay? We are seeing now the final noise, this noise E prime here, is the noise that we had before divided by B, plus something here, right? And what happens...
But you require your secret to be small too, right?
Yes, we are getting there. So what's happening here is that the new noise here that we have E prime, the magnitude, right, the norm, is close to the scaled noise plus this value here, right? Because we want all of this to be close to E over B, we need this secret S to have low norm, okay? So that's the detail here. For this very simple procedure to work, we have to choose S with low norm. But this is fine. The RWE problem is secure if we choose all the coefficients of S to be binary or ternary or very small like this, right?
So
and then if you do...
We have some question here. I have also a question. So let's see. Is it possible to create an LWE-based scheme for any LWE-based scheme and vice versa? So the question is that if we transform an LWE-based scheme to an LWE-based scheme and vice versa.
Well, well, I think, yeah, most of the case, unless you are doing, well, the problem is with RLWE, you have extra properties. We will see soon that we can define slots and rotations. And with LWE, you can also, like, you have this, but it will be really very, very inefficient. So you have the same functionalities, yes, but the efficiency will be much, much lower, right?
Okay, another question. Will modular switching affect input data or computation?
No. So as we are seeing here, right? Input, like the original ciphertext had this M multiplied by Q over T, and the output has M multiplied by Q prime.
So you assume that the modulus is a multiple of the power of B. So
Yeah.
doesn't this affect the security or?
No. The security of the LWE and of the RLWE only depends on the bit length of Q, not on the format of Q. Okay.
Okay.
It's actually simple. I'm presenting you the reason why this is true. Because you can, by yourself, switch from one Q to the other, right? If this doesn't hold here, this, I'm saying that B divides Q is just to simplify the presentation, right?
Yeah, okay, thank you.
Okay, so actually this shows us already how to solve the first problem, right? The noise growth will no longer be exponential. We'll have this situation where the noise growth is kind of like, let's say, constant, right? The noise is kind of not growing, and what is really happening is that we are reducing the ciphertext modulus, right? So this solves the first problem. And now, like, how can we solve the second problem? So this will be a little bit more complicated, but you have to hold strong and stay with me, okay? Because this is more general. If you understand what I'm going to explain now, it will also be easy to understand how the FHE that Ilaria will explain tomorrow works, because it's all about the decomposition that I will explain, okay? So the situation we have now about the noise is solved, but about the degree, right? Remember that we start with ciphertexts. If we represent them as polynomials over this new variable y, the fresh ciphertexts have degree 1, right? But when we multiply two of them, we get ciphertexts with degree 2, right? Because this is just how polynomial multiplication works, right? You multiply them and you increase the degree, right? And now if you multiply degree 2 polynomials, you get degree 4, and then you get degree 8, 16, and so on, right? So with L levels, the degree is 2 to the L on this variable y, okay? So this means that the size of this final ciphertext here, if you have degree 2 to the L, you have 2 to the L plus 1 coefficients, right? But each coefficient is actually an element of this ring here, RQ, right? And the elements of this ring are actually polynomials with n coefficients, and each coefficient is defined mod q. So the number of bits that you need to represent these ciphertexts is this, right? It's essentially 2 to the L times n log Q, right? So the size of the ciphertext is growing exponentially. This means that for efficiency reasons, you cannot compute long, right? Because if this L gets big, then even fetching the ciphertext from the memory will take exponential time, right? It's an exponential number of bits. So you don't want this situation, right? We have to solve this. So the main idea to solve this is the following. Well, when we multiply, we get degree 2 ciphertext. So we want to go back to degree 1, right? That's what we want to do. And then this will guarantee that we will always have degree 1 again. If we multiply degree 2, go back to degree 1, okay? So remember, after the multiplication, the homomorphic multiplication, we get a new ciphertext that has degree 2. So we can write it as like this, degree 2 on Y. Huh? And the property it has is that when you evaluate the ciphertext on S, so on the secret, right, you are replacing Y by S here. What you get is the message plus like the scaled noise, right? The noise times the modulus ciphertext, right? So this is the property we have after the multiplication we just explained, right? So how can we transform this thing that we have here somehow in something that just have 2 coefficients, right? This is what we want to do, right? Somehow we want to get rid of the 3rd coefficient or the 2nd one, doesn't matter, but we want to get rid of some coefficient here, right? The idea is, okay, we know that this holds, right? So what about if we pre-compute this value here, C2 times S squared, we pre-compute it and we include it in C0, right? If we can do this, now we don't need to store this guy here anymore, right? We just store this new C0, right? So this new C0 will be the original C0 plus this C2 times S squared, right? And the C1, the new C1, will be the original C1 that we had, right? Let's say that we can do this somehow. Oops, this, yeah, C0, yeah. Okay, let's say that we can do this somehow, right? We can define this new ciphertext like this, okay? If we can do this, then we can see that if we evaluate this new ciphertext on S, you get this C0 plus C1 times S, right? So C0 is this, C1 times S is just this guy here. So the final expression will be exactly the same as we had here before, right? Because we are already including this in the C0, right? So you can see like C1 prime times S is this guy here, and C0 prime is just the rest that we have here, right? So C prime evaluated on S is the same as the original ciphertext evaluated on S. So this means that this C prime is actually an encryption of M we can somehow take the C2 and multiply by S squared and add this to C0, right? Doing this operation. Then we just need to store this new C0, C0 prime, and the original C1, right? C1 prime. So if we can do this, we are good, right? We go back from degree 2 to degree 1 because the C prime has degree 1, okay? This is what we want to do. But how can we multiply the C2 by S squared? Because S squared is just the square of the secret key, right? So you cannot publish S squared. So we need to do this without publishing S squared, right? But hopefully we have a homomorphic encryption scheme here. So this means that if we publish an encryption with S squared, we can compute on this encryption, right? In particular, we should be able to multiply this encryption of S squared by C2, right? Because it's a homomorphic encryption scheme. So the idea is, well, this is a first idea, okay? Just to get to there. It will not work very well, but it will give us the intuition of how it works. So let's say we define this, I'm calling it as relinearization key, right? And this is just a ciphertext encrypting S squared. So what this means that if I evaluate this ciphertext on S, or the secret, I get some noise times T, right, plus S squared. Right? This is what this means, right? When I generate the keys, I can generate this, no problem, right? Because I know S when I generate the keys. Okay. But again, this means that we have to assume circular security because we are encrypting S squared under S. But this is a detail, okay? Now, we are giving this ciphertext here of degree 2, right? Now, let's say we can take this C2 here, and we can multiply by the relinearization key, okay? And this will give us this C prime here. So this should be an encryption of S squared times C2, right? Because we are multiplying this relinearization key by this C2. If we have an encryption of this is what we wanted actually, right? We wanted C2 times S squared. So now you can just add this ciphertext here to the restriction of this ciphertext. So you take the original one, right? And you add to this new ciphertext here, okay? So you are just defining the C-moot like this. And again, let's see what happens when we evaluate the C-moot on S. If we do this, we get this first part here evaluated on S, so C0 plus C1 times S, right? Plus C prime times S. Sorry, C prime evaluated on S, right? But I said that C prime, I'm hand shaking a lot here, but hand waving a lot here, but let's say C prime is an encryption of C2 times S squared, right? Then this means that when we evaluate it on S, what we get is the message, right? C2 times S squared plus some noise, right? So the noise of C prime I'm calling E prime, okay? But this expression here is just the original ciphertext evaluated on S, right? So this expression here is just some noise plus the message, right? And we have this extra noise here, okay? So this gives us what we want, right? We have now a C-moot that has degree 1 because it's a sum of two polynomials of degree 1. And if I evaluate it on the secret, I get some noise plus the message as we wanted, right? Except that
sorry, what is not clear to me, how do you take out this C prime? Why? Because you need somehow to know the largest coefficient from the ciphertext. This seems difficult.
No, we don't need to know the largest. It's always the C2, right?
Yeah, you need to know C2. But
this you know, right? This is just your ciphertext. You start with a pair, right? If you go back to your definition of the ciphertext, it's just a pair, right? You know these two values. When you multiply, you get three elements. You know the three elements, right? You always know C0, C1, and C2.
The ciphertext weren't of degree n?
Sorry?
The ciphertext weren't supposed to be of degree capital N.
Each of these CIs here are of degree n, right?
Ah, okay, yeah.
They are elements of this ring RQ.
Okay. I see.
Right? So, what I said, we are almost there. The only problem is that, okay, this C-moot here give us, let's say, what we want, some noise plus the message, and it has degree 1, but the noise is actually too big because the noise of the relinearization key was this E bar here, is multiplied by C2. and C2 is just a polynomial uniform mod Q, right? So if we multiply them, the norm will also be close to Q. So this will be way above the decryption failure, right? So that's the problem we have, okay? So, okay, the idea looks promising, let's say, right? We start with this ciphertext that has degree 2 on Y, and encrypts M, and we have this relinearization key that encrypts S square, so we can give away some information about S square, but it's encrypted, so this is secure, right? And then we can try to multiply this relinearization key by C square, and when we do this, we add to the first two components here, and then we get this CMUT. It has degree 1 as we wanted. It's encrypting M, yeah, but the noise of this step here where we multiply the 2 is too big. So that's the problem, right? So we need somehow to solve the problem we have in this first step. Okay? That's where this decomposition comes into scene, right? We need to somehow multiply this value. The size of this value is Q, let's say, right? The coefficients are mod Q, so they are too big. We need to somehow multiply it by this ciphertext without increasing the noise up to Q. So the idea to do this is, instead of multiplying by C2 directly, we first decompose C2 in some base, for example, binary decomposition. This means that we only have 0 and 1, zeros and ones, right? And then we multiply by these binary values, for example, right? Or for the digits that we get out of this decomposition, right? And then, because these digits are much smaller than Q, the final noise will also be much smaller than Q. Okay, that's the idea. So let's say we can fix a decomposition base B. Okay, we can just fix a value B here. Okay, this is not the noise we had before, huh? Just some value B. Okay, just fix. I should have used another letter. I'm sorry. So we just fix a decomposition B here. Okay, this B could be, for example, 2. This means that you want to consider binary decomposition, right? Or this B could be 10, and then you are considering decimal decomposition, right? You can choose it, but it has to be small. And then, okay, this L here is just the number of words that you need in this base to decompose values mod Q, right? Now you can define this vector with all the powers of B up to L minus 1, right? So B to the 0, B to the 1, blah, blah, blah. Now you can see that if we are given any integer, I'm just considering integers for now, modulo Q, now you can decompose them into L values like this, all of them belonging between 0 and B minus 1, right? And if you multiply this vector, compute this inner product, this vector times this gadget vector, what you are doing here is you are multiplying every AI by the corresponding power BI, right? So this will give you back the original value A that you had. And you get A back, right? So but this is general. You can choose the base and this will hold. Now we can extend this for polynomials. Here I'm just considering integers mod Q, but the polynomial is actually just a sequence, a vector, let's say, of integers mod Q, right? So you can take now a polynomial and you output L polynomials with coefficients between 0 and B, okay? So just as before, if you multiply this vector here by the gadget vector, you get the original polynomial A back, right? So your decomposition outputs this vector such that the vector satisfies this property, okay? And now we want to use this decomposition to multiply by some polynomial that is uniform modulo Q without increasing the noise too much. Okay. So let's say that we have a ciphertext C that encrypts M with some noise E. Okay. Now, if we multiply this C by any of these A's here, for example, by A0, right? What you are doing is you are multiplying the message by this A0, but now you are multiplying the noise by this AI as well, right? But now you have the product of two polynomials. You can bound the norm like this. It's just the degree of them times the product of their norms. But now this norm here is no longer Q. This norm here is just B, right? So you get this much smaller bound now. Okay, so what I'm saying here is, if you multiply a ciphertext that encrypts M by any of these digits here, you get a ciphertext that encrypts like AI times M, and the noise is small, right? The noise is somehow close to the original noise that you had before. E, now you just have E times B times N, okay? So let's see how to use this, okay? Instead of just encrypting this message here, let's encrypt this message, I'm calling it mu here, times all the powers of B, okay? So we can define this a vector of ciphertext like this, okay? Every ciphertext CI here encrypts the message times a power of B, okay? So C0 encrypts just mu, C1 encrypts B times mu, C2 encrypts B squared times mu, and so on, okay? You can just define this, right? Let's say we define this. Now, if I'm given any polynomial here, modulo Q, so it's a big polynomial, right? I can decompose it, right? Now I have this vector, and all the entries of this vector are small, right? They have norm bounded by B. And then now I can take this vector here and compute the inner product of this decomposed vector. If I do this, what I'm doing is I'm multiplying A0 by this C0, A1 by this C1, and so on, right? But as I just explained, this AI times CI encrypts the message times AI, right? So each of these terms encrypts something of this form, right? If I add all the L terms, what I get is this message here, right? So I have mu times A0 to the B times B to the 0, right? Plus mu times A1 times B, and so on, right? So I have this summation here. But this sum here is just the original A, right? Because these AIs are the digits of the decomposition of A in the base B. So actually this C that we are defining here encrypts the message we had in the beginning times this big polynomial A here, okay? It encrypts this. But the noise is much smaller. It's not close to Q now. So let's say that each of these initial ciphertexts had noise bounded by some V. As I explained in these slides here, right? When we multiply by this AI, the noise in each of these terms here will be bounded by N times B times V, right? We go from V to N times B times V. And if we add L of them, we multiply this by L further, right? But L is just log Q, so this is also small. So this means that if instead of starting with a single encryption of mu, we start with L encryptions of mu, but not only mu times the powers of these bases. If we start with this, then we can multiply by any coefficient we want, by any polynomial we want, right? We just decompose the ring element first, and then we perform this inner product, And what we obtain is an encryption of mu times the value that we wanted to multiply, okay? And the noise will now be small, okay? So back to our relinearization key. Instead of defining it as one single ciphertext, we define it as L ciphertext, right? Just like here, okay? So each ciphertext here encrypts S squared, but multiplied by a power of B, okay? Now, when we have this ciphertext with degree 2 that we had before, right? We want to multiply the S squared by C2, right? But we just saw how to do it. Now we decompose C2. Product with the relinearization key. So now this is truly an encryption of C2 times S squared with a small noise. And then we just do as we did in the first attempt, right? We restrict the original ciphertext and we add the C prime to it. And as we saw before, if we evaluate this on S, we get a noise plus the message. But the difference is that now this noise here is small. It's just log Q times N times this B, which we can choose to be small, times this V, which we can also choose to be small. And this is way, 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 way smaller than the Q. Okay? So that's how the relinearization works. You will start from this degree 2 polynomial. You have your key. You decompose only one ring element here, C2, and we perform this in a product. So at the end, what you obtain is the CMUT, and it has this degree 1 as desired, okay? So the trick here, that you really have to understand is this trick here, right? That if instead of starting from a single encryption of mu, you start from L encryptions of mu, right? Because you have now mu times all the possible powers of your base encrypted, right? That's the trick. Because if you start from this, now you can decompose your ciphertext on this base and you can perform this multiplication, okay? That's the trick, the decomposition trick. This will be used by FHE tomorrow on this external product, okay? This is used in the another schemes like GSW. This is used basically everywhere because it's a general trick to multiply homomorphic ciphertext by a big value, a large value, without increasing the noise too much, okay? So now the homomorphic multiplication works like this. During the key generation, so just to recap, in the very beginning, we tried to say, okay, homomorphic multiplication, let's just multiply the ciphertext, right? And then we had two problems. One was the noise growth was too big. So for this, we developed the modulo switching. The other one was the degree was also growing exponentially, right? And for this, we have now a solution, which is the relinearization, right? So how the relinearization works? First of all, you have to prepare this key, right? We call this the relinearization key. And this is a set of encryptions, right? A set of ciphertexts, each of them encrypting S squared times some power of B. So you do this during key generation, and you can publish this, right? Because it's a set of ciphertexts, it's fine. You can just publish them and it's secure. And then you do this one single time, right? And then for every multiplication, now you have two steps. First, you perform the multiplication itself, as we saw, right? But now you get 3 elements instead of 2 elements, right? And then you know that these elements satisfy this relation, and then you run this procedure that we call relinearization, right? This means essentially you take your relinearization key, and then you take one of these elements here, you decompose, and you compute the inner product as we just saw. But this, what is important is that these maps your 3 elements back into a pair of elements, right? And then, because this operation here, relinearization, preserves the message, if the message here is the product of the 2 messages, the final message is still the product of the 2 messages, okay? So now this is how we multiply. And on top of that, of course, we also want to perform the modulo switching to reduce the noise, okay? So we started from this very simple and naive homomorphic multiplication, which was actually just this step here, right? Just multiply the ciphertext and see what happens. And now we see that on top of that, we need this relinearization and we need the modulo switching. Okay, so now that's essentially it. Huh? We know how to construct FHE schemes whose ciphertexts are compact because of the relinearization and whose noise grows slowly because of the modulo switching. Huh? And this is essentially how the BGV or the CKKS or the FV or many schemes work. Okay, so if you go there to open FHE or HElib, the libraries that implement these schemes, you will see BGV, you see relinearization there, you already know what it means, right? It means that somehow you have to generate this key which encrypts the square of the secret key in the beginning of the process, and then after the multiplications, you have to run this relinearization and modulo switching. Okay, so does anyone have question now? Because this, maybe it was a bit hard.
Yeah, any questions? I have a question. So in CCK,
CKKS.
No, the GSW, the multiplication is asymmetric. So you take a ciphertext and then apply a function on the second ciphertext, which comes from this decomposition techniques. So, but in the explanation that you mentioned, I didn't see this asymmetry in your multiplication.
No.
So here, the multiplication is symmetric.
Yeah, because I mean the main idea is the same. It's still decomposing the ciphertexts, but in the very end, what happens in the GSW is that you don't have this relinearization key. You kind of put this relinearization key. Yes, and then you can decompose the ciphertext directly when you multiply.
So here, the ciphertext doesn't grow, right?
No.
Okay.
But I mean, in their case, I mean, what it means by it grows is that it's just that the ciphertext is bigger than here in our case from the beginning, right?
Yeah.
But when you do this multiplication, you kind of inflate the ciphertext, you multiply, and then you get something that is big, but it's the original size again, right?
Yeah.
It's still compact in the sense that the ciphertext size is not changing within the homomorphic evaluation, right?
Okay. And this scheme that you described, who has designed it? Or
this main ideas,
the one that you described.
Yeah, the main came from this BGV scheme, right? It's Barkesk, Gentry, and Vaikal. Yeah. It's a hard name. Sorry.
Vaikal, I think.
Yes.
So it's for this scheme BGV that you explained.
So the relinearization, I think they were the first scheme to describe this, but the relinearization applies to basically all schemes, right? For CKKS, for FV. The modulo switching also for sure was described the first time on this paper, BGV, but CKKS has essentially the same procedure, modulo switching. It's basically the same. It has just a little tweak there, but it's mostly the same. And FV doesn't have modulo scheme but they have something that is very similar at the end to the modulo switching. So if you understand this modulo switching, you take the description of the other schemes, you will understand them fairly easily.
Okay, thank you. There is also a question in the chat box. Can we apply similar tricks in AGCD-based FHE?
So in AGCD-based, yeah, there are some attempts. There is this relinearization here, for example. Oh, sorry. This modulo switching, for example, was proposed by Professor John Sebastian Corum and other authors. But yeah, you don't get the same efficiency at the end. Huh? But you can, at least the modulo switching, you can. The relinearization is not really necessary because since there you just work with integers. When you multiply two integers, you get another integer, right? When you multiply two polynomials, you get another polynomial, but the degree is increasing. When you multiply two integers modulo q, it's always modulo q, so the size is not growing. So essentially, you don't really need this relinearization unless you are constructing your scheme in a very original way, let's say.
Okay. So, and now the development of new ideas for accelerating these FHE schemes. I think, has there been any new idea recently, or what is the most scheme, the most, the fastest scheme? I think it's for 2018, right? Have we had any other recent ideas?
Okay.
So my question is that somehow it seems that we have got stuck in a state that we cannot go further. Is my understanding correct?
Well, I would not say stuck, but it's true that many new schemes are building up on other schemes, right? But they are not like, how you say this, breaking the ground, right?
Yeah, so they are somehow.
But we will have some discussion about this at the end. Huh?
Okay.
Okay.
Let's continue.
So how much time I still have, please?
We have about 2 minutes left, so I don't know.
2 minutes?
Yeah.
Okay, sorry. Take too much time. I was just going to talk about this. This is lots. It's essentially that our plain text space if you think about I don't know, you multiply matrices, your entries are integers, so they are not polynomials, right? Your programs, you sort a vector of integers, whatever you do is over integers. So there is a trick to, you just have to decompose, to factor this polynomial modulo t, modulo the plain text modulos you have. And then because you factor these, you get many polynomials of low degree. And then your plain text space can be written as this direct product here, right? And this allows you to encrypt many integers, one in each slot here, instead of encrypting a big polynomial, okay? So in general, you can do this. You can have S slots, and this means that now you can encrypt S integers, mod t, instead of a polynomial. And when you perform an addition of a multiplication, what you are doing is you are operating entry-wise. So you are adding or multiplying these values in each entry, right? So this gives you this nice property that now you evaluate a function one single time, but you are actually inside your ciphertext, you are evaluating the function in every slot. You see? So we call this single instruction multiple data. Now, if you perform the homomorphic evaluation one time, you are actually performing this in every slot. Okay, so you are, it saves you a factor of S, right? If S is the number of slots. So instead of running S homomorphic evaluations, you just run one time, and this acts already over the S. And well, there is also something that you can rotate the slots, but this is pretty close to the relinearization that I just showed. Okay, you can prepare a rotation key, we call it key switching key, just like the relinearization key, and you can use it to rotate the slots. Okay, so just to finish it, yeah, so more or less, like, this is a summary of the schemes that we have. Okay, I am already in the 2 last slides, so I'm just going to finish it. Okay. So for example, BGV and FV, they are kind of similar. They allow you to encrypt a vector of a vector using these slots, right? So you can encrypt a vector of integers mod t for nt you choose. So it has slots, and the bootstrapping is very expensive. And the key material you need for the bootstrapping is about some gigabytes, right? The CKKS is similar, but it's not integers mod t. The message space is real numbers up to some precision, of course, right? And then the bootstrapping is also expensive, and the key material is also huge. And then you have this new family of schemes. It's TFHE and concrete. It doesn't have slots, so you can only encrypt one single small integer. So integer mod t, this t has to be very small, like 3 bits, for example, right? And now the bootstrapping is really cheap, and the key material is just some megabytes, but you are packing less information in each ciphertext. Binary messages, right? And the bootstrapping is even cheaper than with the FHE. And this is just a summary of the libraries if you want to play with this with these schemes, right? So you can take this table, check the libraries. This is the language where they are implemented. User-friendly, it's, well, user-friendly for me. Maybe it's not user-friendly for you, but anyway. And asterisk here means that the bootstrapping is implemented in the library, or it's not implemented in the library, okay? Okay, guys, so that was it for today. I hope this will help you out.
Yeah, thank you, Hilder, for your nice talk. It was really, really excellent and very informative. So we have a couple of questions. Maybe we can finish the talk with this. Is there any real-life scenario with where each party has their private input to belong to 0 and 1 and want to secretly compute a function? So I think somebody has answered. In e-voting, we have this application. Does this come from Chinese reminder theorem? So
yes.
I think, yeah, that's
exactly, yes. It's just a general version of the Chinese reminder theorem, right? Because, I mean, the first way we learn it is just decomposition of their integers, right? But this is just an ideal, right, over this ring, so we can decompose again.
What are the ideas involved in packing ciphertext where one can do multiplication and addition efficiently?
The ideas involved, well, the base is just the CRT, right? The Chinese reminder theorem, as someone spotted, right? And once you have this, you know that this is an isomorphism, and then the isomorphism is actually already giving you this entry-wise addition and multiplication, right? And then, yeah, this increases the efficiency because, for example, let's say you have 1,000 slots. This means that you can now encrypt 1,000 messages, integer messages, in one single ciphertext, right? And then you evaluate the function one single time, but you are actually evaluating the function like under the hoods. It's equivalent to evaluating the function 1,000 times, right? So you are saving a factor of 1,000.
Okay. So, Hilder, you should be very tired. You have spoken for 2 hours, but it was really, really very good for all of us. So we thank you, and I hope
you,
that
guys.
I have the opportunity to hear the rest of your talk in some other occasions.
Yeah, like I'm sorry, I got a little bit like I didn't manage the time very well because I allowed you to make questions on the way, so I lost a bit track of the time. But anyways, this last part was already, I had already planned it to be very high level. The hard part was the modulo switching and this relinearization. Okay, you can see that this other part is very high level.
Okay, thank you. So we will be here in 25 minutes for the next talk. Goodbye.
Okay,
Goodbye.
thank you very much.
Goodbye. Thank you.
Bye.